Hello. It's time to return to ridiculously huge numbers. I'm going to call this making the most of the fast growing hierarchy. And it's really going to be a revisiting of numbers that and notions that came up in my big previous series. But I want to start from the basics, and we're really going to start from the basics. And I wanted to make it self-contained, at least in principle. It's going to help if you've seen very basic ways of making fast growing functions and huge numbers like the Knuth up arrow notation would help, because I'm going to go kind of quickly at that level, but I will go through that level. But we're going to go very, very far. We're going to go well past Graham's number and tree of three, if you've heard of those famously big numbers. But I want to avoid a lot of what really turns out to be unnecessary sophistication if the main goal is to create fast growing functions and the big numbers that come out of those. So part of the point here is to show what we can do with an extremely limited set of notions. So more specifically, here's what I'm going to do. I'm going to revisit territory that like I said, starts with the basics and starts with the very lowest levels of what's called the fast-growing hierarchy of functions. But then the goal is to get up to the territory from Stanley Wainer's article that's called slow growing versus fast growing. And this, again, this was in like video, I don't know, 46 or something of the previous huge series. Technically, this uses a concept called tree ordinals, but we're going to invent them on the fly and never actually even call them that, because it really, you don't have to think about them that way. It's really based on very simple notions, just used in a very clever way. Similarly, it's secretly, we're going to get to what are called ordinal collapsing functions, but they're just, you don't have to know about those. We won't actually even use the usual notion of ordinals and ordinal arithmetic, even though this reinvents the crucial part of that, the part that's necessary for us, like I said, on the fly. And as I've said in the other series, part of this is it's kind of like one of those fractal zooms where you just sit and you watch it come at you, and it's just like this amazing complexity, and then, oh, you zoom in more and there's more complexity, you zoom in more and there's more complexity. And so I'm going to show, as I did in a lot of the other videos, some big computations that kind of get bigger and bigger, and the complexity grows, and you get this tiny, tiny, tiny little bit of a glimmer of the massive explosion of complexity that happens with these functions. They start from a very simple seed, and then when you unpack them, it's amazing. I guess it's like the TARDIS in Doctor Who. It's like it looks small on the outside. You start unpacking it, it's absolutely amazing. And like I said in the other videos, like part of this is just for the 10-year-old and all of us, just big numbers. Wow. And how do you get those in really a very elegant way? There's wonderful connections that I'm not an expert into, theory of computation and proof theory. And if some people want to leave in the comments, like things like, how does this all translate to like lambda calculus and type theory and things like that, that'd be cool. But I'm really not going to focus on the theory. It's really going to try to keep it as low tech as possible while producing some super big numbers. Now, for the Googology purists, the Googology enthusiasts, I'm not going to go nearly as far as the sort of state of the art there, because that does go further and further in this ordinal collapsing function story. And I don't know if it's possible to take the stripped down kind of ideas that I'm showing here and really go that far. But it's not that we're not going to take it to the absolute outer limits of the numbers of people thought of, and we're not going nowhere near Busy Beaver or Rayo's number, because that's not the idea here. This is all very, very much based on computable functions. Because I have a fondness for those. I think they're much more grounded and they're much more concrete, even though there's a lot of abstraction as well, but it's a different kind of abstraction. So what are the basics? Let me just, in the rest of this video, just get it started, and then we'll do the more details in the next one. So we're going to create a world from a single seed, just a 0. We're just going to start with 0. And we don't even have to know anything about 0. We have 2 fundamental operations, and that's create a function. So we do have to have some notion of what a function is, something it takes inputs and produces outputs. And then we have to have the notion of successor, which informally means add 1. Just count on to the next thing, add 1. What we'll see is we'll add 1 to objects that we wouldn't necessarily know we can add 1 to, and we'll sometimes talk about that as just put a successor marker on some object. But this will all become clear as we go. And really, really key is that we can repeat each of those operations indefinitely, and we're going to alternate them in a very clever way. That's really the whole thing. So you can stop watching the video now, I guess. Okay. So at stage 1, our first thing, we're just going to use successors. We're going to start with 0, and we're just going to say the next thing after 0, the next thing after that, the next thing after that, the next thing after that. And of course, we usually write that as 0, 0 plus 1, 0 plus 1 plus 1, 0 plus 1 plus 1 plus 1. And of course, we have standard abbreviations for that. And that's 0, 1, 2, 3, etc. We've just invented the set of the natural numbers. Okay, so not an unreasonable place to start. Usually, we have this nice notation with like what's called blackboard bold version of capital N. We're going to call it big omega sub 0 or omega naught. And that will fit into a whole hierarchy of sets of sort of fancier and fancier kinds of numbers. They're really going to be, most of them are going to be funky function constructs, but we'll kind of think of them as fancy kind of numbers. And we'll eventually fit into a hierarchy, omega 1, omega 2, etc. If you have seen the big omega in the context of like uncountable ordinals, they sort of are secretly sort of that, but they're not the same thing. So don't assume that this is something that you've seen in that context. Right now, omega naught is just a notation of the natural numbers, and we'll get to the other stuff. Okay. So our main goal, we want to create a world of ridiculously fast-growing functions from the natural numbers, omega naught, to itself. That is our goal. And then we will put in some moderately, not even very big, input into one of those functions to create the ridiculously big numbers. So we're going to start small, and we just create. It's going to be a family of functions, right? So they're going to have for now they're going to start with the very standard function notation f. And then the first input, I often call that the control input, is which function we're talking about. And then the next is the ordinary input, just like what number is being put into this function. So this is the 0th f function, and we're applying it to some number n, and it's just think of that idea of successor and make it into a function. Just say, well, systematically, if I could do it to any particular number, what happens if I just think of it as a function that takes any possible number and produces its successor? It's just n plus 1 in the most ordinary way of f of n is n plus 1. Okay, but sometimes I'll want to abbreviate and forget that it's a part of a family and has this index 0 and just call it s of n, the successor function. Okay, very simple. What's the next stage? The next stage is to repeat that an arbitrary number of times. And that is so much the heart of, well, it's one of the hearts, I guess, one of the key ideas here. And so that means that f, the 1 version, so f of 1 something, f of 1n, it uses the f of 0 function, but it does it n times. So first of all, you put n as the input, which is not absolutely essential to this kind of stuff. The main important thing is we're doing the previous function many times, but you might as well put in n is the input number as well. So we put in n in the input number, and we put it into the f of 0, in other words, the successor function. And then we do that again and again and again and again, and we specifically repeat that n times. And it's really crucial that we're repeating it more times the bigger n is. And we don't have to be any fancy. We could like say, oh, n squared times. Nah, that's not gonna help us much. We don't need to do that. We're gonna get big functions, big numbers without ad hoc kind of stuff. It's supposed to be really elegant is the point. So what's a more compact way to write? What is this idea? This is the idea of iteration, that any function that has the same kind of output as it has as an input, you can repeat it. Okay, just cycle through and do it again and again. So what's a more compact way to write that? We use a superscript, right? So whenever we have a function and we just want a simple way of saying repeat that n times, like this s function, we're going to put that in as a superscript. So that just is an abbreviation for s of s of s of s of s of n, with the s repeated n times. And of course, if we really need to remember it's a specific member of this family, this is a very common notation in math, where if you've got some function that you're used to having the input filled with a specific dummy variable like n, and you specifically want to just say, well, what about the function? And I don't even want to name the dummy variable. I want to just say, what is the function? It's the zeroth function in the f, and we want to leave kind of an open slot. Then that's what this dot says. So this is just the function that's ready to accept an n input or whatever input. And I do that function n times. Okay. So this kind of notation, we're going to see this a lot, where I have like f of like 7 comma dot, which is just f, the 7th function in the f sequence of functions with an open slot. So, okay, now what are we doing? This is nothing new. This is n, and then I take one, I take that and take n plus 1 plus 1 plus 1, and I add on n ones. Well, guess what? We've just reinvented doubling. Not really shocking. Okay, so this is just doubling in a fancy way, but of course we're setting this up to be extended in a massive way. So that's going to be, sometimes I'll abbreviate that function, the f of 1 something function, as just d for doubling. Okay, so we created the f of 1 function as repeat the f of 0 function. And now we're going to do that again. We're just going to do a lot of repetition in this story. Okay, so f of 2 comma n is just take the f of 1 something function and iterate it n times. Now, what does that mean? Right? It means at the first level, we're just really doing f of 1 comma n. And then we take that and we put it into the f of 1 comma something function. And then we put that into the f of 1 comma something function. Or if we use the abbreviation d, we're just doing d of 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 n, and we're specifically repeating d n times. What are we doing? We're taking n and we're doubling it n times. We do have an ordinary notation for that. It's completely, this is a subset of ordinary arithmetic. We're not creating anything really new here, just with a different perspective. And we can write that as n times 2 to the n, and all the rules that we know for that really do apply. Okay, although you could prove it just from just the very tiny little bit that I've shown you. This can be stripped down to an incredibly simple formal system. Okay, so this is a bit faster growing, right? So we've got 2 to the n here, multiplying n. And so I'm going to call that, I'm going to abbreviate that as e of n, because it's got an exponential nature to it. And this is already something that people would say, like math teachers like me would say, this is a fast growing function, right? Exponential growth, like the economy is growing exponentially. You see this in the newspaper. So already, even with the tiniest bit of this idea, we've got something that compared to ordinary, in an ordinary context, it usually is fairly fast growing, right? When an epidemic grows exponentially, it matters. So for example, what are some of the values here? We're going to see a few of these values. What the rare times when we're able to really ground things at really super explicit numbers beyond this stage, we might see these numbers show up again. When you plug in 1 into one of these functions, it's pretty much always degenerate. We're just exponentiating 1. So we're taking 1 and we're doubling it, but just one time. So all we're doing is the doubling function. Well, really, that's actually, if you strip it all the way back, it's just really just taking the successor of 1 you're going to get to. So it really breaks down into something pretty basic. Okay, f of 2 is you start with 2, you double it twice, good old 8, not so huge. If you start with 3 and you double 3 times, so that's 3 times 8, you get 24. If you double, let's just look at, I'm going to look at 8 because we'll see that coming up in a second. There's a reason why I want these next two values. If you double 8 times, you get 8 times 2 to the 8, happens to be 2 to the 11th, and that happens to be 2048. not super significant, but we can see it's getting, you know, a little bigger. Okay. We're going to need this one in a sec. F of 2 comma 24, or in other words, the exponential doubling thingy applied to 24. So 24 times 2 to the 24, 3 times 2 to the 27, about 400 million. So what some people think of as a big number, utterly trivial by the standards of what we're going to get to, even pretty soon, much less later. Okay. So we can keep doing this, right? So this is, again, this is the lowest levels of what's called the fast-growing hierarchy, or the Wiener hierarchy, or Gregorczyk Wiener, something like that. So f of 3 comma n means let's do the 2-level version of f, the f of 2 blah function. We'll do that n times. Now, I still have a convenient abbreviation for that, e of n to the n. Okay, so this is going to be iterated exponentiation. So if you've seen Tetration or Knuth double up arrows, that's the level we're at. But it's a one variable function. It's not like two things combining, because that's just simpler. I'll abbreviate as t of n because it's kind of like Tetration. So let's see what we get. Okay, f of 3 of 1, or we're going to call that t of 1. Well, what's that going to do? It's just e applied one time to 1. Oh, wait, we already know that. It just degenerates all the way back to 1 plus 1 is 2. Okay, so again, that's that degeneration. But I'm not going to do that one too many more times. F of 3 comma 2, already we're starting to see a little bit of power. I'm often going to be putting 2's in as the inputs when we get to a new function and we want to get some intuitive sense by just plugging in a number. I'm going to plug in 2 fairly often, because if you plug in even 3 or more, it explodes too fast often. Now, I'll try to plug in some 3's and maybe even some 4's, but we're going to often get at least a bit of a sense from just plugging in 2's. Here, the 2 still isn't terribly impressive. This is the t of 2, that's e repeated twice of 2. We just had e of 2 happen to be equal 8, and I happen to have e of 8 in my back pocket. That's 2048. Let me actually write it out kind of to show the kind of recursive structure. Again, this tiny little idea of like zooming into the fractal kind of thing. It's 2 times 2 times 2, right? So that's the e of 2 part. And then you take that the answer of that, and you put it into the input of the next exponential. So you get that thing times 2 to itself, and then that eventually becomes 2048. Okay, so that idea of sort of layers and layers of an onion maybe or something is really there. Okay, we're going to wrap this up in a sec, but I want to kind of get through the tetration level. F of 3, or the tetration level f function of 3, e of 3, or e of 24, or e of 24 times 2 to the 24. Or if I want to make it a little more explicit, 24 times 2 to the 24 times 2 to the 24 times 2 to the 24. Or if I really want to back up even further and show that the structure just with the 3's and the 2's, so you take 3, you double that 3 times, then you store that result, and then you take it and double it that many times, store that result, take it and double it that many times. Well, that's getting pretty big. Now, if you just look at what's going to make it really, really big, it's this last bit. It's 2 to the 3 with a heck of a lot more. So this is way bigger, really, than 2 to the 3. But that's kind of the heart of what's going to make it big when you go further. So we could express that when we don't want to have such tiny little exponents. And we're going to see, I'm going to have to sort of zoom in and out and probably change the magnification of the screen sometimes so that we can sort of see exponents and then maybe extract them out. So one way to write that would be define a function which is 2 to the x. And this is a fairly good way to write that. Just this is kind of like the dot notation. This is just the 2 to the something function applied 3 times. There's that iteration again of 3. And if you know the double up notation, then that's going to be it's bigger than 2 to the 2, which is 2 double up 4. So if you want to compare it to that and you don't know it, then look up my first few videos in the other big series, or anybody's videos or any Wikipedia on Knuth up arrows. But I'm betting a lot of people watching it have at least seen that. So one more explicit one here at the 3 level, tetration of 4. So that's do the exponentiation guy for 4 times. So you start with 4, you double it 4 times. Then you store that, you double it that many times. You store that, you double it that many times. And you store that whole thing. And I think I need one more. Yeah, that's just a copy of that guy. So sorry. There we go. That's the real thing. Okay. And I think the next one's probably right. Yeah. Oops. So that's bigger than 2 to the 2 to the 2 to the 2 to the 4. Rather bigger. But I'm extracting out the really crucial thing, which is bigger. Well, that's equal to the raised 2 to the power done 4 times on 4. So that's bigger than 2 double up 5. So that shows you this really is roughly at a tetration level with base 2, or a double up arrow level with base 2. So that's just the very beginnings, but we've seen the first idea, and really a couple ideas. One, which is iterate and build on what you've already done. And that's sort of recursively iterating. The new function iterates the previous version of the function, which is defined by iterating the previous version of the function, which iterates the previous version of the function. So that whole refer to the previous version of the function is a recursive idea. And then there's just straight up iteration, like a for loop in a simple programming language, which is the just let's repeat this a certain number of times. And even that, combining recursion and iteration already is very powerful, but we're going to see that there's another idea we'll put it in with, we'll combine it with very soon.